happen here? Because since the chemical shifts are so similar, they're both on the benzene ring, what happens is that these move into each other. I didn't talk about coupling constants, but these move towards each other. And as they move towards each other, because the chemical shifts are so similar, the inner peaks grow at the expense of the outer peaks. So what I actually get is this. I get a signal that looks like this. That's not a great diagram. I get a signal that looks like this. This is often referred to as an A-B quartet. It's not the normal quartet, which is 1 to 3 to 3 to 1. And there's also a space here. So it's not 1 to 3 to 3 to 1, which is the way a normal quartet looks. 1 to 3 to 3 to 1. Right? And no space, no significant space between them. I get, this could be anything from 1 to 2 or 1 to whatever. And there's a little gap between them. So basically it's a deformed doublet of doublets. So as these get closer, these grow. That's called an AB quartet. So if I see an AB quartet for 4 H's, that is a para-unsymmetrical benzene ring. Okay, so we have spectral patterns that are aliphatic, spectral patterns that are aromatic, and the last thing we do is look at some special chemical shifts that reoccur. And so 0.9 speaks to a methyl that is unperturbed. 1.2 is a methylene that is not anywhere near to groups that push or pull electrons. 1.5 is for a methine that is not anywhere near to things that push or pull electrons. 2.4 suggests H attached to carbon attached to carbonyl. It also is H attached to a carbon attached to benzene. Not the H directly attached to the benzene ring, but the H attached to carbon attached to benzene ring. Between about 4.5 and 6, you have H attached to a carbon-carbon double bond. Yeah, okay, so 3.5. So 3.5 would be H attached to carbon attached to O, or H attached to carbon attached to Cl. And then 4.5 to 6 is H attached to carbon-carbon double bond. And then between about 6.5 to about 7.5 is the H attached directly to a benzene ring. And what's happening with the benzene ring here, this is shielding by anisotropic effects, right? And then 9 to 10, these are aldehydic H's. And then 11 to about 12, those are H's of carboxylic acids. And that's a combination of both induction, some resonance, but largely this is a combination of also anisotropic effects. So it's anisotropy. This falls in the de-shielding cone, but it's also subject to the inductive effects of the O. Whereas this is in the de-shielding cone, but it's subject only to the inductive effects of the carbon, the C+, C delta plus. Right, so those are some telltale chemical shifts, those are good guides for things to look at that should jump out at you when you look at the NMR spectrum. Okay, so we'll stop here and we will start looking at spectra to analyze the next period. Thank you.